Here are solutions to homework set number 2 for ECE 320 for spring 23. The first question deals with semiconductors. When you dope a semiconductor, you have p-type and n-type. If I put the two types together, I get a diode. So I've got two types of silicon doping. Here's p-type, here's n-type. The symbol is that. The symbol is kind of a reminder. Current flows P to N, but not N to P. Or in terms of anode-cathode, again, this is the anode, that's the cathode. Current flows anode to cathode, not cathode to anode. How come? Well, there's a couple different answers. As far as I'm concerned, any of these are fine. As long as it makes sense to you, it works. One explanation is as current flows P to N, I'm using majority carriers. Since there are a large number of carriers, I have very low resistance. If I try to have current flowing backwards, I'm using minority carriers. There just aren't very many of them. With very few carriers means very high resistance. So essentially a diode is a variable resistor, low resistance P to N, high resistance N to P. Second explanation is at the PN junction, there is a depletion zone. Almost all the holes in this region get swept to the right. Almost all the electrons in this region get swept to the right. You've got diffusion from high concentration to low concentration. The net result is I have this depletion zone. The depletion zone means there's an insulator, no current can flow because there's no charge carriers. If I apply voltage anode to cathode, I take that depletion zone and squeeze it to zero. Once it's zero, it conducts. If I apply voltage the other way, I just make the depletion zone bigger. So again, still no current flow. Third explanation is with those charge carriers diffusing, I have a whole bunch of plus charges over here. I have a whole bunch of minus charges. That winds up with about a 0.7 volt potential energy barrier. That's for silicon. Different materials have different potential energy barriers. But there's about a 0.7 volt potential energy barrier across this. I need at least 0.7 volts for current to flow. Those last two are kind of nice because the way the current flows through a diode is actually kind of like this. It takes about 0.7 volts for silicon to conduct, and you can explain that with the depletion zone or potential energy barrier. The majority-minority carriers, it's kind of hard to see why you need 0.7 for it to carry current, but you do. So any of those are fine. Pick your favorite. Problem 1. Problem 2 looks at doping. Suppose I just have a piece of silicon. It's a 1206 resistor, so it's got certain dimensions. I want it to be 3,300 ohms. How much doping do I need? Well, I know the resistance is resistivity times length over area. Solving, I want a resistance of 156 ohm centimeters. 1 over the resistivity is the conductivity. That's equal to the number of charge carriers times the charge per carrier times mobility. This is phosphorus, n-type. So there's the mobility of electrons. Here's the charge per carrier. Solve for n. I wind up with a doping of 30 times 10 to the 12th atoms per cubic centimeter. That seems like a large number, but actually it's not. Avogadro's number is 6.02 times 10 to the 23rd. That's the number of atoms in a cubic centimeter of 1 mole. So I've got 10 to the 23rd atoms. 10 to the 12th of them are phosphorus. So you see that it's a really, really small percentage of the atoms are actually phosphorus. But those few phosphorus atoms are important. They provide the charge carriers that allow it to carry current. They're what makes the resistance 3,300 ohms. Problem 3. If I go to DigiKey, here's DigiKey, kind of the toy store for electrical engineers. I type in this part number. I want to find this part. It's a specific thermistor. If you look for thermistors, like right here, search for thermistors, time passes. DigiKey currently sells 11,795 negative temperature coefficient thermistors, and they range anywhere between 0.7 ohms and like 50,000 ohms. type in a very specific thermistor. So here I'm going to search for this part number. And here it is. This is what it looks like. Cost 29 cents each. 0 in stock. DITCHI is kind of nice. They summarize it. The two numbers we want is 3.3 kiloohms at 25 Celsius. And here's the B number, 4,500 degrees Kelvin. Again, this is lower k, 1,000. This is capital K, Kelvin. Causes some confusion. That's all you need. If you click on the data sheets, here are the data sheets for that part, how you order it. From here, you've got the resistance at 25 Celsius. Here's the one we're looking at. There's the B value. No, maybe not the one we're looking at. Anyway, there's the B value. That's really the only two numbers you need in the data sheet. And there's more information here. I really just care about those two numbers. What those two numbers tell me is that here's the model for the thermistor. It's 3,300 ohms, 4,500 Kelvin. So what the equation looks like is this. This is my B number. This is degrees Kelvin. If I have temperature in Celsius, Celsius plus 273 gives you Kelvin. 25 Celsius is 298. At 25 Celsius, these two numbers are the same. They cancel. I get 0. E to the 0 is 1. That's the resistance at 25 Celsius. So anyway, that's what that equation means. With it, I can plug in numbers. If I take 0 degrees Fahrenheit, convert to Celsius, joys of living in America, we have weird units. Convert to the international units, 17 degrees Celsius, plug it in, and I get 41 kiloohms. At 40 degrees Fahrenheit, the temperature of your refrigerator is 10 kiloohms. 68 degrees Fahrenheit, temperature of cold water is 4 kiloohms. And 120 Fahrenheit, temperature of hot water, 1 kiloohm. That's the beauty of thermistors. There is a large change in resistance, makes it actually fairly easy to tell you what the temperature is based upon the measured resistance. And just for fun, I didn't ask for this, but if you want to plot the temperature versus resistance, I can do that in MATLAB. If I have the Fahrenheit, temperature goes 0 to 120. Celsius is Fahrenheit minus 32 over 1.8. That's the conversion from Fahrenheit to Celsius, which in the equation is called T. Here's my equation. Plug it in. I've got to use the dot slash because that tells MATLAB don't do element by element division or matrix inverse. Treat this as just a whole bunch of numbers. Then plot temperature versus resistance in kiloohms. And here's what you get. So it's a big change. That's one of the nice things about thermistors. There is a large change in resistance as temperature changes. They're very sensitive. Okay, on to problem 4. Problem 4 is if you go to Circuit Lab, click on a diode, like a 4004 diode. So here's Circuit Lab. I grab a diode, drag and drop, double click on it. I can change the diode. And these two numbers, IS, that's the current IDSS, and N, that's the number we're looking at. The number in the denominator is N times 0.026. 0.026 is the function temperature, Boltzmann's constant. There's a couple other terms in here, just create a slightly more accurate model. And depending upon which diode you use, you get slightly different numbers. All diodes are really about the same. Yeah, slight difference. But anyway, that's where these two numbers come from. So that number and this one. This is NVT, that's the 1.45. And VT is 0.026 at room temperature. So multiply them all out, I get 0.0377. There's the current versus voltage relationship for a 4004 diode. If I have this circuit, I want to find the current and the voltage. I've got two equations, two unknowns. One equation is the diode equation. The second equation comes from the circuit. So from the circuit, if the current is 0, x-axis, the voltage across the diode is 5 volts. That's right here. If the voltage is 0, the y-axis, I have 5 volts over 50 ohms, 100 milliamps. 2 points determines a line. This is called the load line. We do a lot of load lines in this class, if I can spell line correctly. Where the two intersect is your solution. That's one way to solve two equations, two unknowns. Second way to solve is to solve numerically. What I'm going to do is use a function called fmin_search. I'm first going to come up with a function where I guess the voltage, and kind of going back over here, I'm going to guess the voltage, compare these two, and keep iterating until the difference is 0. And actually, it probably works better if you guess the current, but I'm going to guess voltage. So here's my function. I'm going to guess the voltage. That's VD. From that, I can find the current through the diode. From the load line, I can find the current from the load line. The error is the difference in the two. Let's see. And display my guess, the log of the error squared, return. That's a function of MATLAB. So I can now guess again, or let MATLAB guess for me. That's the function fmin_search. I'm going to minimize this function. My initial guess is 1 volt. Go. And it comes back saying that the voltage is actually 0.8221, and the minimum, the sum squared error, is 9 times 10 to the minus 6. Pretty much 0. So that's the second way to solve, using numerical methods like fmin_search. Third way to solve, throw it in MATLAB. And MATLAB does exactly the same thing we did back in problem 4. It iterates until the currents balance, tells what voltage makes the current balance, and the current is actually 779 millivolts, not 822 millivolts. Yeah, pretty much the same thing. Fourth way to solve, build the circuit. So here's one of the 5-volt powered breadboards for your lab kit. When I plug it in, I need to move this jumper up here. On the bottom, it's 3.3 volts. Up high, it is 5 volts. So I've got 5 volts on this line, ground on the second line. It's going to go from 5 volts through my 100 ohm resistor, or 50 ohm resistor. I actually used 51 ohms. Here's my diode. There's the little line. On the diode, it's got this symbol on it. That symbol is this guy. That tells you which way the current flows. This is the forward direction on the diode. Going to ground, so here's 0 volts. Measure the voltage, I get 757 millivolts. So I can compare them. If I use a graphical method, here's the voltage, numerical solution, simulation circuit, lab. This is typical in 320. I've got one circuit, I've got 4 different answers. Each method uses slightly different assumptions, so the answers are slightly different. They should be close though. So it's at 800, 821, 779, 757 millivolts. It's right around 700, 800 millivolts, ballpark. And the current's really all about the same. So that's one approach, with 2 diodes. Suppose instead I have 3 diodes. In this case, the resistors I grabbed were 100, 150, and 220 ohms. Find the currents ID1, ID2, ID3, 3 different ways. Now in this one, I don't use graphical methods because I don't know how to draw in 6 dimensions, so skip that method. I can use numerical methods. With numerical methods, I'm going to guess the voltage V1, V2, V3. From that, calculate the currents, ID1, ID2, ID3, and then do my node equations. At node 1, the currents have to balance. At node 2, the currents balance. Node 3, the currents balance. So starting out, going anode to cathode, if I know the voltages, I know the current, ID1, is the voltage anode to cathode. For diode 2, it goes anode to cathode, V1 minus V2. Diode 3, anode to cathode, V3 minus 0. So those are my 3 diode equations. They depend upon the circuit. The node equations then. At node 1, I've got the current left, which is minus ID1. Current down, plus ID2. This current, V1 minus V3 over 150, plus this current, V1 minus 0 over 220. has to be 0. Likewise at node 2, likewise at node 3. Solve. So to solve, what I'm going to do is, same as before, this is now called diode 3. I create a function in MATLAB. I'm going to pass a vector. What z means, it's a 3 by 1 vector. What it means is that's my guesses on voltage, V1, V2, V3. Once I know the voltages, I can find the current through the diode. I can do my node equations. The error should be 0. If they're not 0, if my guess is wrong, it's a non-zero error. Have j return the sum squared error. Keep iterating until the error is 0, or minimize j. So if I throw that in MATLAB and have fn search solve, it tries to solve what's the solution to my function called diode 3. My initial guess is 3 volts, 2 volts, 1 volt. It iterates and says, this is what I found, and there's the sum squared error. The sum squared error is almost 0, meaning that's probably the right answer. And so that's what I get using numerical methods. Second approach is throw it in Circuit Lab. Build the circuit in Circuit Lab, tell it what is the voltage, V1, V2, V3. I get those 3 numbers. Third approach is build the circuit. So here is 5 volts right here, that line. This is 0 volts, the blue line. This node, the way these boards are built, these are shorted up and down. So this node right here is V1. This node right here is V2. And V3 is right here. So measuring V1, V2, V3 with a voltmeter, I wind up with these readings, V1, V2, V3. My V0 isn't 5 volts. My 5 volt regulator isn't perfect. That's what I actually cut for 5 volts. If you notice, again, the voltages are similar. 4.19, 4.22, 4.14 for V1, 3.41, 3.49, 3.40 for V2, 800 millivolts, 758 millivolts, 755 millivolts, V3. 3 different answers for the same circuit. Again, typical in 320. Each method is going to give you slightly different answers. If they're close, you probably did it right. If they're way, way off, probably what happened is I took one of the diodes and flipped it. It's in backwards. That's typically what happens. But anyway, that is homework set number 2 for ECE 320.